Yeah. Hi everyone. This is Shishira Reddy. Let's discuss about the visualizing Kannada Nest with PCA. These are our teammates. And coming to the introduction, we have Kannada Nest dataset. It contains 28 by 28 pixel grayscale images of handwritten Kannada digits. It contains 60,000 training and 10,000 test images. And coming to the high dimensionality, each image has 784 features, making it difficult to visualize and analyze. PCA overview. Coming to PCA identifies principal components that capture the most variance, reducing the data's complexity while retaining key information. The main goal is use PCA to project the 784 dimensional data to two dimensions, visualizing the data in a 2D scatter plot for better understanding and insights. Thank you. Next, continued by my teammate.
Hello everyone, my name is Vaishnavi, and now it is turn for the what is dimensionality reduction. And the dimensionality reduction is a technique that reduces the number of features in a dataset while maintaining key information. It is crucial for high dimensional data to avoid issues like there are three issues that is slow training, it has the more features required, more computation, and harder interpretation. It requires the high dimensional data is difficult to analyze, and the curse of dimensionality. As the feature increase, modeling and visualization become challenging. Here, techniques like PCA help reduce these problems by simplifying the data. And next, when we go to the wide dimensionality reduction with PCA, we have three things that simplifies the data. It reduces the features while preserving most of the data variance. And the next one is the visualizes data. It projects high dimensional data into 2D or 3D for easy visualization and reveals pattern. It identifies trends, clusters, or structures within the data. For the Canada Menace dataset, PC reduced the 784 features to two components, making it possible to visualize the data on the 2D plane. And next will be continued by my teammate. Thank you.
Hi everyone, this is Pratisha. When it comes to understanding PCA, PCA identifies the principal components, directions of maximum variance in the data, becoming the new axis for the reduced set. So in this we have three steps, that is covariance matrix, eigenvalue, eigenvectors, and projection. When it comes to covariance matrix, computes it computes how futures vary with each other. So the eigenvalue and eigenvectors find principal components that and the variance they explain. So the projection projects the data onto these principal components to reduce dimensionality. The key idea is that the first principal component, the PCI, captures the most variance, with the subsequent component capturing progressively less. So when we go to the next slide, applying PCA to Canada Mist. Using scikit-learn for PCA, it is implemented. The implementation is based on singular value decomposition, a method used to factorize matrices and extract the principal components. In this, we have the steps like we need to load the data. We need to load the data from the Canada Menace dataset, and we need to pre-process the data. We need to normalize the data that is used for performance and ensure all features are on the similar scale. So then we need to apply PCA. The data is transformed into a lower dimensional space in 2D case. So the next will be continued by my teammate. Thank you.
Yeah, hello everyone. Today I will be discussing principal component analysis or PCA, how it helps us visualizing the Kadana Mist dataset. First, let's talk about PCA. PCA is a dimensionally reduction technique that transforms our data into new datasets, uncorrelated features called principal compounds. In this case, we focused on two principal compounds. The first principal compound or PC1 is reference direction in which dataset visits the most, and it It's where most variation is captured. And the second principal component is uh, orthogonal or to capture the second highest variance. By using PCA, we reduce the data set to just two dimensions, resulting in 2D projection. This allows us to visualize our data in two ways that maximize spreads or variance among points. And go to the next slide. Yeah, now when we plot these two components, each data sample with reference digits is color coded based on this class from 0 to 9. As you can see, this scatter plot shows distinct clusters where each cluster corresponds to different digits. For example, all sample reference digit 1 tends to each group, so samples represents other digits. Then, yeah, this clustering helps us visualizing separate digit groups, showing PCS power to reveal patterns in complex data. Yeah, thank you. Next slides will be continued by my friend.
Shishira, one second. Can you please go to the slide insights? Yeah, thank you. Coming to the insights from the PCA visualization, cluster analysis, the PCA plot often reveals clear separations between the digit classes such as 0, 1, 7, and etc. And next is the interpretation. Similar digits examples 1 and 7 are placed closer to each other in the 2D space, suggesting that PCA has captured the relevant structure of the data. Next to the PCA effectiveness, the visualized structure helps in understanding the data better and guides further analysis or model building. Next slide, please. These are the limitations of PCA for Kannada MIST. First one is the linear assumptions. PCA assumes that the data lies on the linear subspace. It may not perform well if the data is not linearly distributed. Second one is the information loss. Reducing the dimensionality to 2D results in some loss of information, especially if the variance in the data is not evenly distributed. And next is the alternatives. Nonlinear methods like TSNE and UMAP can be used to better clustering, but they come at an computational cost. Thank you. And next slides will be continued by Fanindra.
Okay, thank you, Ramya. And I will be taking through the code that we have used for principal component analysis of Kannada MIST. And firstly, we are importing the libraries that are required. Next, we are loading and reading the data. Here we can see the data labels for the number and the pixels. The dimension number of pixels are 785 for each digit. And the next we will be selecting the label and the features, where Y we have taken the label and X all the pixels columns. And next is the standardizing the data with the standard scalar. And we'll be importing and applying the PCA. Here we would be projecting from 784 to 2 dimensions with the PCA.fit transform method. And the PCA variance ratio is 0.079 and 0.055. Then we plot the two principal components of each point to learn about the data, where you can see here the principal component 1 and the principal component 2. In this plot, we have taken from 784 dimensional point cloud, and these color points are the projections of each data along the directions with the large variance. Now we'll be using the three principal components. So the data, the variance ratio for the three components is 0.079 and 0.055 and 0.04 for the third one. Then choosing the right number of components. The thumb rule for choosing the right number of components is to add up to sufficiently large portion of variance. Example, it is 95%. And with the n number of n components, we give the 0.09 and we plot the PCA with the number of components and the cumulative variance. This is the graph. And PCA, now we will be plotting the original train data without noise. So we can see clearly here with the binary map, using the binary map. The next is with the noise. When we plot with the noise, we can see it in this. So training the data set with PCA on noise data, it is letting to preserve 50% of the variance. %50 of variance amounts of 24 principal components. And this is the inverse of the transformation of reconstruct the filtered digits. Can we go back to the conclusion? So in conclusion, the PCA successfully reduces the high dimensional Kannada mist data sets to 2 dimensions for visualization, as we have seen from 784 to 2 dimensions. The scatter plot reveals the underlying structure of the data. PCA is a good starting point for dimensionality reduction through other techniques might be necessary for more complex data. Thank you.